Here's another video for to the lecture intropde. In this video we present section 5.6. Section 5.6 presents the solution in even dimensions again by the method of descent. So we now generalize to arbitrary even dimensions the method of descent and go down from the dimension from n+1 to dimension n. This means we consider initial values g and h as functions on Rn+1 just by combining the map. We have two maps. Yeah, we have x n+1 coordinate of Rn+1. This maps to x bar, and this is just x1 where we neglect the last component, the n+1 component. And then by considering for f and g, g and h, for g and h function on Rn going to R, you have a map x going to g of x bar and x going to h of x bar. This we call g bar and this we call h bar. These are functions on g and h. Yeah, and okay, and then we solve the initial value problems for these functions. Yeah, and then we see indeed that that the corresponding solution is also independent of it. This follows from this consideration. Yeah, if we have a function f which doesn't depend on the last coordinate, so that this partial derivative vanishes, then the same is true for the mean. Yeah, because if we calculate the mean over the spheres, then we may write this in this form, put the integral in, and we see then this mean also doesn't depend on x+1. Yeah, so if we take the solutions, yeah, so if we take now the solutions, also if we use these initial values here and calculate also the corresponding solution of the homogeneous wave equation, also does not depend on xn+1. So it's also of the form, therefore it is of the form u of x bar t of a solution u Rn cross Rn +0 to R of the initial value problem in dimension n. Okay, and so now we want to calculate this function, yeah, and we use again the same idea as we did it for dimension 2. Yeah, we use this parametrization. So the idea is rather clear. We have here the dimension, let's say n dimension here, and this is xn plus 1. Okay, and now we have here this ball in the n-dimensional ball, and then we want to calculate the hemispheres in n plus 1 dimension. Yeah, and for this reason, so this is the ball in xt in Rn, and we want to map. We have a map psi, yeah, which maps this ball bxt to the ball of to the boundary of the ball. Yeah, and this map is again exactly of this form. So this is completely analogous. Yeah, psi of y is just equal to y and then plus minus gamma of y with gamma of y, gamma of y is just equal to square root of t square minus y minus x bar. Okay, and then we calculate this again. This gives this expression, and so this is just this determinant. Yeah, gradient 1 plus gradient y gamma of y square, and then the square root of, yeah, this is just this is 1 plus y minus x bar divided by t square minus y minus x bar square, and this is of course the and square. Yeah, so we get t square. On the bottom we have t square minus y minus x bar square, and on the top term we have t square minus y minus x bar square plus y minus x bar square. Sorry, here we should write, yeah, we should take the square of the whole thing, and then we see this is this, and this is of course t square divided by t square minus y minus x bar square. And if we take the square root, we get an extra t. Yeah, so this is, so we obtain here this formula. Yeah, this is then the formula. Yeah, 2 times, because we have both hemispheres and we have this additional t, and yeah, so we obtain the formula that mean over the sphere, over the n plus 1 dimensional sphere xt, f bar y d sigma of y, this is now equal to 2t omega n divided n plus 1 omega n plus 1 and the sphere fy dny square root of t square minus y minus x bar square. Yeah, just by using our formulas for this integral. Yeah, this is the 2t, and of course these are the difference of the means, and so we have this formula. Now now we can state the main formula for a solution in even dimensions. Yeah, so the initial value problem is solved by this formula. So the only thing which remains to be understood is this factor in front. Yeah, this factor in front. And in order to understand this factor in front, we have to calculate this quotient here. Yeah. So now we want to calculate this quotient. In order to calculate this quotient, we again use our parameterization. So we know that this is, of course, n plus 1, yeah, omega n plus 1 times Rn. This is the volume of the boundary of the sphere. Oh, sorry, here is missing a boundary of the sphere. So let me... okay, so we integrate the function 1, yeah, over the boundary of this ball. This is the boundary of the ball in n plus 1 dimensions, d sigma of y. And now we use our parameterization. Yeah, 2 times in lower and upper hemisphere, then dny over the, now we calculate over the ball in Rn, yeah, and we have this factor r square minus y square. Yeah, this is this formula with this factor where we choose the ball around 0. Yeah, then this simplifies to this term. Okay, and now this, of course, we can write as 2r integral from 0 to r, and now we integrate over the balls b but s, the boundary of the balls with here. Here is again missing a boundary, yeah, because now we use this polar coordinate. So let me again correct this. Okay, now I corrected this. Okay, this is this boundary times dn. Sorry, and then it's also not dn, but it's d sigma of y divided by square root of r square minus s square. Yeah, because y square is then of course s square on this ball, and then we have ds. Okay, now since this integral does only depend on s and not on y, we may perform this integral, and then we get 2r, we leave outside, we get 0 to r, and then this integral here, taking this integral over this ball, this just gives n omega n s to the power of n minus 1 ds divided by square root of r square minus s square. Okay, and now we make a substitution. Yeah, now we make a substitution. And what we substitute? We substitute rx is equal square root of r square minus s square divided by r. Yeah, then this is of course the same. If we put the r inside the square root, then we get 1 minus s over r square. Yeah, s over r square. And then we see clearly that dx we may calculate dx if we take the derivative with respect to s, then we obtain dx is equal to taking the derivative is we get minus s over r times square root of r square minus s square. Okay, and this is okay. This means now if we let's calculate this again. Moment, simplify. This is our substitution, so this means rx is equal to square root of r square minus s square. So we have r dx is equal to minus 2s ds times 2 square root of r square minus s square, 1/2 for the square root. So, and this is the same as minus s ds over r times x. So r dx is this expression. And now we want, okay, and what is s? S is of course the same as if we take here this formula, if we take the square, this is x square, and then we have here r squared divided 1 minus s over r squared. So s over r is of course square root of 1 minus x squared, and so we have s is equal to r square root of 1 minus x squared. So now we insert this in this formula. So this means here we insert this. So now we continue here with this. This is 2r, then integral from 0 from r. Now what we have here, n omega n. Now 0, if we calculate x, 0 corresponds to, if s is 0, then rx is equal to r, so x is equal to 1. And if s is equal to r, then x is equal to 0. So we get rid of the minus by reversing the order, and then we get integral of from 0 to 1. 0 to 1. S equal 0 corresponds to x equal 1, and s equal r corresponds to x equal 0. Okay, so, and we replace the two borders, and then we get rid of the minus, so we have n omega n. Now s ds is equal r dx, is equal s ds, so we have s, which is 1 minus x squared. Now how many powers we remain? We have n minus 2, so n minus 2 over 2. And how many powers of r. So we have r to the power n minus 2. And then we have here an additional power times r times dx. Okay, and the r dx here, this is exactly the square root which we have here. So we indeed remain with this integral. And so what is it? The 2 remains, so let's put it out. 2 r to the power of n altogether times n omega n integral from 0 to 1 from 1 minus x squared n minus 2 over 2 dx. Yeah, so we end up here with this formula. Yeah, and now we want to calculate this integral. Now let's calculate this integral here. Yeah, and how to calculate the integral from 0 to 1 minus x squared to the power of m, yeah, dx. Now we do a partial integration. So partial integration, so we say this is 1 times this function. So this is x times 1 minus x squared to the power of m from 0 to 1. And now minus, but the inner derivative is of course plus m. Then we have 2, so 2m, and integral from 0 to 1. And we have x, and inner derivative is also x, so we get x squared 1 minus x squared to the power of m minus 2 dx. Okay, now this is clearly 0. This is 0, so we only have this term. Yeah, this was partial integration. Now we only have this term, and but this term we may write as minus 1 minus x squared, yeah. So x squared minus 1 plus 1. And x squared minus 1 is of course the same as minus 2m integral from 0 to 1, 1 minus x squared to the power of m dx. And then we have in the rest term is plus 2m integral from 0 to 1, and now it's just 1 minus x squared m minus 2 dx. And now we may put this on the left hand side, add this and divide by 1 plus 2m. So we get 2m divided by 2m plus 1 integral from 0 to 1, 1 minus x squared m dx, m minus 2 dx. So this is now a nice formula. In particular, this means now we inductively may apply this formula. So what we get, yeah, we get 2m divided by 2m plus 1. In the next situation, yeah, we get 2m minus 2 divided 2m minus 1, and so on. And of course, what is the last factor? Yeah, until when m is 2, yeah, then this goes away. So the last factor is just the bottom term is 1 and the top term is 2. 1 and 2. Yeah, and if this is 1, then this is just 1. So we may write this, of course. Yeah, this is 2 to the power of m times m faculty divided by, okay, and then we have here again 2m plus 1 faculty, but then we have these factors we have to multiply out. So we get this. So this is our result for this integral. Yeah. So what does this mean for our formula before? Now, if we look at this formula, or maybe we do it here. Yeah, if we look at this formula here, yeah, what we then see? Then we see, if we divide this, then we get, so n plus 1, omega n plus 1, and divided by 2n omega n. Yeah, and the Rn and Rn cancels. This is integral from 0 to 1, from 1 minus x squared times n minus 2 over 2 dx. So this is m. So, and m is here, of course, n is even. So this is really an integer. Yeah. So what we get, we should insert for m. Yeah, m is equal to n minus 2 over 2. Yeah, so we get this is now 2 to the power n minus 2 over 2 times n minus 2 over 2 faculty divided by, and what is 2m plus 1? This is, of course, 2m is n minus 1, so this is n minus 1 faculty. N minus 1 faculty. So this is now the result for this number. And if we now insert the formula here, if we insert the formula for the n plus 1 dimensional wave equation, yeah, then we have, so we should now use these factors, yeah, but so this is, we obtain u of xt is equal 2 to the power, and now n plus 1 minus 3. This is n minus 2 over 2 times n minus 2 over 2 faculty divided by n minus 2 faculty, and then this whole expression. But in addition, yeah, we have now this factor here. Yeah, so we have, in addition, we have this factor. Yeah, by our formula here. Sorry. Here. So we have in addition this factor. So by 2 omega n divided by n plus 1 omega n plus 1. And then we have an extra t. This we should keep in mind. Okay, now what does this give? Yeah, since we have this number, sorry, here, this should be squared. Okay, so what does this give? Yeah, we have this, so we insert this. So we have 2 to the power n minus 2 over 2, n minus 2 over 2 faculty divided by n minus 2 faculty. And now we should insert this factor. Yeah, so we should divide by this. So we get n minus 1 faculty, 2 to the n minus 2 over 2, n minus 2 over 2 faculty, the whole thing square. Yeah, And so this is the constant which we have to evaluate. Yeah, then we see, of course, all this cancels, and here it remains an extra n. Sorry, here we have an n minus. Okay, sorry, here we made a mistake. Yeah, if you look in this formula, then we have here an n minus 2, but this n should be n plus 1. Yeah, so here this should be n plus 1, n plus 1 minus 2, and we also have, here we have to be careful, here we have this factor, but before we calculated with this factor, yeah, so we get here an extra n. We get here an extra n, and this we write as n half times 2. Okay, now let's do the calculation. Of course, this cancels with this. This is n plus 1, this cancels with this. So what we get 1 divided by n half. Yeah, this is 1 divided by 2 times n half times 2 to the power of n minus 2 half, and n minus 2 half faculty. Now n half times n minus 2 faculty, this is of course n half faculty. N is yeah even, and here we have an extra factor, so this is the same as 2 n half and n half faculty. So in this way we indeed get we cover this factor here. Yeah, we cover this factor, and now this power, to understand this power, yeah, the power in here was in our formula was Tn minus 2. So n plus 1 minus 2 is n minus 1. But we have this additional t, so we get t to the power of n. Okay, so this is, for this reason we get this power t to the power of n in our formula. Yeah, here t to the power of n. So this explains this formula, and this proves now this theory. Yeah, so we have now the formula for all even dimensions. Yeah, and of course again now by this formula we see the length of the speed of propagation is bounded. This time it's bounded by 1. Yeah, because we have an integral over the since u of xt depends on the values of g and h on the whole ball xt. Okay. So the speed, not on the boundary, then the speed would have length 1, but on the whole ball. So and the differentiability, yeah, we see again we have to apply n here for n minus n half differential operators on G and n minus 2 half on H. Yeah, so we have it's times less differentiable as G, n half less differential as T, and n minus 2 times less differentiable as H. Okay, so we close this section. Finally, we want to show that that for any k, the solution in dimension, in one dimension less, one odd dimension less, yeah, we want to show that the method of descent also works going down from even dimension to odd dimensions if we go further down, yeah. So if we may restrict further, we can also go down further, and this follows here. So if we do the same procedure, yeah, we do the same procedure by going down, and we show now that the mean with this extra weight here of a function which doesn't depend on the third variable, on the last variable, also doesn't depend on the last variable. Yeah, this shows this formula. So the same line of arguments apply. Yeah? Since this mean on the ball with this weight doesn't destroy this property. Yeah? Does not depend on the last coordinate if the function f doesn't depend on the last coordinate. Okay, so we can go down further. And now we want to calculate. And now we want to calculate the solution. We want to recover the solution for odd dimension, but one less than the even dimension by the method of descent. So this time we have to evaluate on the whole ball, yeah, but the function we have to take the mean of the ball. So let's now calculate the mean of the ball in this radius for a function which does not depend on the last variable. Yeah, so we consider, maybe I draw a picture to explain this. Yeah, so the picture is here again. We have this, we have downstairs here, we have this ball downstairs. Okay, and then we, so this is the ball in n dimensions, and this is the ball in one higher dimension. And since the function doesn't depend on this coordinate, yeah, this is the coordinate xn plus 1, we may integrate here along all these lines here. Yeah, we may integrate, we calculate the length of these lines, and then we integrate over the lower dimensional ball. So by this method, yeah, we can integrate this integral over the ball, over the n plus 1 dimensional ball. We transform it to an integral over the n dimensional ball. Okay, so this should be this. Now we want to integrate this over this ball, but we know, since f doesn't depend on the last function, yeah, we can take here this integral. Yeah, so we let's do the calculation. B0t. This is now the n+1 dimensional ball. And this is the function which doesn't depend on the last coordinate. Yeah, so we have to calculate this by dn+1y. Okay, and since f does not depend on the last coordinate, we can do it as an integral over the n-dimensional ball, t, and an integral over these lines. But these lines clearly go from minus square root of t square minus y square bis plus square root of t square minus y square. And then we have this factor, dy n+1 divided by square root over t square minus y bar square minus yn+1 square. Yeah, because this is clearly y square. And then integral, and then times f of x bar plus y bar, and now it's only an n-dimensional integral, y bar. Okay, and now we make a substitution. Yeah, we make the substitution. We call z equal to yn+1 divided by square root of t square minus y bar square. Okay, so then what is, yeah, then dn+1 is then clearly dz. Okay, what is the integration variable? Y and z. Yeah, so we have, this is clearly dz times square root of t square minus y bar square. Okay, and now we have to calculate this. The square root of t square minus y bar square minus yn+1 square. What is this? And I claim this is clearly square root of t square minus y bar square times, and now we have 1 minus yn+1 over 1 minus yn+1 over yn+1 square over t square minus y bar square. Yeah, and okay. Yeah, because if we multiply this, then we get here this t minus 1 minus this term. Okay, and this is clearly, so this is square root of t square minus y bar square times, and this is just square root of 1 minus z square. Okay, now we can insert. Now we can integrate. Insert this, and then we can integrate this. Yeah, so we insert this. So this integral here. Yeah, what is with the integral here? What we get for this integral? T square minus y square. If we this is the variable yn, yeah? The new variable z then corresponds to -1 and +1, yeah? yn+1 equals plus minus square root of t square minus y square. This corresponds clearly to z equal to plus minus 1. Okay, so this integral here, so the integral from minus square root t square minus y bar square plus t square minus y bar square, and then this whole thing dyn+1 divided by square root t square minus y bar square minus yn plus 1 square. So what we get by this substitution, this is integral from minus 1 to plus 1. This dyn, yeah, this is dz, this is dz times square root of t square minus y bar square, t square minus y bar square. And this whole term here, this term is just square root over t square minus y bar square times square root 1 minus z square. So you see, this simplifies minus 1, 1 dz over square root over 1 minus z square. Very simple. This simplifies to this. Okay, and everything else doesn't depend on yn plus 1. So we can perform this integral. Yeah, and this integral, what is it? It's clearly, so arc sine is an antiderivative of this function, so we get just pi. Yeah, we just get pi, and for this reason, now we can calculate this, and we all together get we all together get that our integral here is just pi integral over ball t f of y bar dny. Okay, now we insert this in our formula. Yeah, now we insert this in our formula, and so we obtain u of xt is equal okay, so we obtain pi. Now we just use the, as before, these factors, but now we should replace the dimension n, the even dimension n, yeah, in this formula. In our here, this should be n plus 1. So 2n plus 1 half times n plus 1 half faculty. Okay, this is the factor in front, and then we have then we have d by dt, and then t times t by dt to the power now n minus 1 half. Okay, integral over ball bxt of g of y dny plus the same for without this t times d by dt n minus 1 half integral h of y dny ball bxt. Okay, and now now we can perform one differential. Now we use again this polar coordinates. Yeah, now we use again this polar coordinates, and then we see if we do here the derivative, yeah, then we get moment, here we have also some factor omega n plus 1. Yeah, because we have the mean. Yeah, because we have the mean, and we added the corresponding powers of t. Yeah, also we replaced the mean, of course, by omega n plus 1, and then the corresponding powers of t. Yeah, also in this formula here in dimension, here in the even dimension, sorry, here in the even dimension, here, no, in this formula, yeah, we have this t to the power of n, yeah, t to the power of n, but this is of course exactly the dimension of this ball. So we instead of the mean, yeah, we divide only by omega n plus 1, yeah, and then we get rid of these factors. Okay, now we use take here the derivative. Yeah, now so this should be omega n. Omega n. This should be faculty. Now we take calculate this derivative. So this is pi. Here we have this factor n plus 1 half. N plus 1 half faculty times omega n. And no, omega n plus 1, of course. N plus 1. And now if we do the calculation, yeah, then taking the derivative is of course by polar coordinates. We get d by dt. We have d by dt. Now we have n minus 3 half. And okay, and then we want to get the mean in dimension n, but we have one t less, so we have tn minus 2. Yeah. So then we have to add here an omega n. Yeah, since if we calculate this, we get t to the power n minus 1, and then 1 over t, sorry, 1 over t. 1 over t. And here also 1 over t. Yeah, for this reason we only have the power tn minus 2. And then, yeah, then we have the mean of g of y d and y over the boundary of the ball. Yeah, also if we take the derivative, yeah, then this is exactly this volume with this one inverse power of t. And of course the same thing for this should be not an integral, but this should be a bracket, and then we have the same thing, 1 over t d by dt n minus 3 half t to the power n minus 2, but without this and mean of h of y d n y over the boundary of the ball xt. So now we are almost done. Yeah, the only thing which has to be which we have to check is that this factor pi omega n 2 to the power n plus 1 half n plus 1 half faculty omega n plus 1, this has to be now this other factor, yeah, this has to be this should be, yeah, that we recover the formula of dimension n, of odd dimension, yeah, then it should be this factor. So this should be, this is what we have to prove, n minus 3 half times n minus 3 half faculty divided by n minus 2 faculty. Okay, and how we prove this? By the same method as before. Yeah, yeah. So yeah, this time, yeah. So here we show that this is indeed the inverse of this factor. Ah, yeah, this p. Okay, and we just show, and this we do by calculating this. And in order to calculate this, we again use the same formulas as we had before, but now for numbers m which are half integers. Yeah, and then we get then we have this formula again. We have the same induction, but for half integers we then get, we get n minus 2 over n minus 1. So this means integral over 1 minus x squared n half minus 2 dx from 0 to 1. This is now n minus 2 over n minus 1 if we get 1 less. So we have altogether n minus 2. These are now odd numbers, yeah, and then we have finally 2, 1, and here we have finally maybe 3 and 2, and then we can add here an additional 1. So what we get this time here, this is an n minus 2 faculty, and then we have n minus 1 half. Yes, we have an n minus 1 half, and in the bottom we have one factor more. Yeah, we have one factor more. So we have n minus 2 faculty. So the last factor we just this n minus 1 we just write here, and then we have the additional factors. Yeah, then we have for the additional factors. So we have n minus 3, so we have 2 to the power n minus 3 half, n minus 3 half faculty, and the whole thing times n minus 1. And finally, the last integral, which I missed, sorry, yeah, of course, we also get a final integral, and what remains finally is the integral from 0 to 1 dx over square root over 1 minus x squared. Yeah, and this is of course p half. Yeah, this is p half, and by this then we get this factor, and if we insert this factor, then we indeed recover the same formula as before. So we indeed get this coefficient. Yeah, so we get this inequality by this recursion formula. So we see indeed that we can obtain by the method of descent all lower dimensions. Now we may iterate this application of the method of descent, and so this means by this iteration we get all the formulas in lower dimension by inserting initial values which only depends on the first m variables for arbitrary number m which is smaller than n. Yeah, for an arbitrary m smaller than n, we may take this initial values which only depends on this variables m in n dimension, and then this gives the solution in m dimensions. Yeah, so the method of descent also works going down from even dimension to odd dimension, or more general from arbitrary dimensions to all lower dimensions. Okay, what we have shown today, we have solved in general the homogeneous wave equation in even dimensions by the method of descent, and obtained a nice formula for even dimensions. Yeah, this is the formula which we obtained for even dimensions. It's written in this theorem here with this constant in front, and we showed that we can go down even from the even dimensions by the method to descend to the odd dimensions. Yeah, and maybe here for even, this even works to go down to the dimension n equals 1. Yeah, but then one should use this first formula, because otherwise this would become negative exponents. But here then this becomes 0, and then we can calculate this derivative very easily in dimension 1, because then by the fundamental theorem, yeah, we use again polar coordinates and use the fundamental theorem of calculus, and then we see we really recover in one dimension D'Alembert's formula. So thank you.